Hello everyone, welcome to this lesson. In this chapter, we are going to talk about one of the most important topics in networking, Ethernet LANs. Before we go deeper into technical details, I want you to first understand the bigger picture, because when you understand the big picture, all the smaller details will start to make much more sense. Most computer networks today can be divided into two main types: local area networks, which we say also LANs, and wide area networks, which we say also WANs. Let's start with local area networks. A LAN is used to connect devices that are physically close to each other. For example, devices in the same room, devices in the same office, in the same building, or even a group of buildings in a campus environment. In a local area network, devices can communicate very quickly because the distance between them is small and the network is usually controlled by a single organization. So another type of this network is wide area network. A wide area network is used to connect devices that are far apart. This could mean connecting different cities, connecting different regions, or even different countries. The internet itself is the biggest example of a wide area network. Unlike LANs, WANs are more complex because data has to travel long distance and through multiple networks and devices. Now, here is a key idea you need to remember. LANs and WANs don't work separately. They work together to form a complex network. So, for example, your computer connects to a local network, your local area network, and connects to a wider network like the internet. So when you open a website, your data first moves inside your local area network and then travels across wide area networks until it reaches the destination. And the main goal of these networks is very simple: to deliver data from one device to another accurately, efficiently, and reliably. So, in this chapter, we are going to focus specifically on LANs and more precisely Ethernet LANs. Because Ethernet is the most widely used local area network technology in the world, understanding Ethernet means understanding how most real world networks actually operate. And this knowledge is essential not only for passing the CCNA exam, but also for working in real networking environment. So let's continue and explore how Ethernet LANs really work. Now let's look at the type of LANs. To understand this better, let's go back to a simple real life situation. Imagine you are in an office or at home. You have multiple devices around you: your laptop, your smartphone, maybe a smart TV, or even a printer. Now the question is, how are all these devices connected to the network? Today, most networks use two main types of local area network technologies: Ethernet LANs and wireless LANs. Let's start with Ethernet LANs. In an Ethernet LAN, devices are connected using physical cables. These cables can be made of copper or fiber. Copper cables use electrical signals, while fiber cables use light to transmit data. Because Ethernet uses physical cables, it is often called a wired network. Now, why is this important? Because this physical connection provides a direct path between the device and the network. This makes communication faster, more stable, and less affected by external factors. So, wireless LAN is another type of this network. So, as the name suggests, wireless networks don't use the cables. Instead, they use radio waves to transmit data between devices. The most common example of this is Wi-Fi. When you connect your phone or laptop to Wi-Fi, you are using a wireless LAN. This gives you flexibility. You can move around freely without being physically connected by a cable. But here's the important trade-off. Wireless communication is more sensitive to interference. Walls, distance, other devices, and even environmental factors can affect signal quality. This means wireless connections can sometimes be slower or less stable than wired ones. Now, here's a key insight you should remember. Ethernet and wireless are not competitors. They complement each other. In most real-world networks, both are used together. For example, in an office, desktop computers and servers are usually connected using Ethernet cables for maximum performance and reliability. At the same time, employees use Wi-Fi on their laptops and phones for flexibility and mobility. So both technologies serve different needs. Now you might ask that if wireless is more convenient, why do we still focus so much on Ethernet? The answer is simple. Ethernet provides high speed, lower latency, more stable connection, and better reliability. This is especially important in enterprise environments and critical systems. That's why in this chapter we focus mainly on Ethernet LANs. Because if you understand Ethernet, you understand the foundation of most real-world networks. And once you understand that foundation, learning wireless and other technologies becomes much easier. So let's continue and go deeper into how Ethernet actually works. So now let's understand a typical small network. To make this easier, let's imagine a real situation. You are at home or in a small office. You have several devices, laptop, phone, maybe printer, or maybe a smart TV. All these devices need to connect to the internet and also sometimes communicate with each other. This type of network is called SOHO network, which stands for small office, home office. It is one of the most common types of networks in the world. Now, question is, how do all these devices connect together? In a traditional setup, we use a device called a switch. A switch is a central device that allows multiple devices to connect to the same network. Think of it like a meeting point. Each device connects to the switch using an Ethernet cable. Your computer, your printer, and other wired devices all connect to the switch. The switch then manages how data flows between these devices. For example, if your computer wants to send data to a printer, it sends the data to the switch, and the switch forwards it to the correct device. This makes communication inside the network fast and efficient. In addition to internal communication, your network also needs access to the internet. This is where a router comes in. The router connects your local network to external networks like the internet. It acts like a gateway. It decides how data leaves your network and how incoming data enters to your network. Now, here's something important. In modern Soho networks, you usually don't see separate devices for switch and routers. Instead, they are combined into a single device. You probably have this device at home. It is often called a router, but in real it performs multiple functions. It provides internet access with routing function, Wi-Fi connectivity with wireless access point function, multiple Ethernet points with switch function. So inside one device, you actually have a router, a switch, and a wireless access point together. This integration makes small networks much simpler to set up and manage. You don't need advanced configuration or multiple devices. Just plug in your internet cable, connect your devices, and the network starts working. Now, here is a key idea. A Soho network is simple in design, but it includes all the fundamental components of larger networks. It has devices like end host. It has switching, which provides local communication. It has routing, which provides internet access as well. So, by understanding Soho networks, you are actually learning the foundation of much larger enterprise networks. And once you understand this foundation, it becomes much easier to scale your knowledge to more complex environments. So in the next section, we will take this concept and expand it into enterprise level networks. Now let's scale this idea to a large environment. So far, we talked about small networks like home or small offices, but in real life, many organizations are much bigger. Think about a company with hundreds or even thousands of employees. They may have multiple floors, they may have multiple buildings, or many different departments. In this case, the network becomes much more complex. Instead of having just one switch, we now have multiple switches distributed across the building. Typically, each floor has its own switch. Why? Because devices on that floor, computers, printers, IP phones, need a local point to connect to the network. This local switch is often called an access switch because it provides access to end devices. Now, if each floor has its own switch, we need a way to connect all these switches together. This is where a central switch comes in. This central device is often called a distribution switch. Its job to connect all access switches and allow communication between them. Now let's walk through a real example. Imagine a computer on the third floor wants to send data to a computer on the second floor. What will be happen? First, the data goes from the computer to the local switch on the first floor. This is the access switch. Then the switch checks where the destination is. Since the destination is not on the same switch, it forwards the data to the distribution switch. The distribution switch acts like a central hub. It receives the data and decides where to send it next. Then it forwards the data to the switch on the second floor. Finally, the second floor switch delivers the data to the destination computer. So the path looks like this: source device, access switch, distribution switch, and destination device. Now, this design is very powerful because it allows the network to scale easily. If you add a new flow, you simply add a new switch and connect it to the distribution layer. You don't need to redesign the entire network now, so you don't need to build everything from the beginning. So you don't need to change anything. Just add your new access switch and connect it to distribution switch. Now let's talk about wireless. In modern enterprise networks, wired connections are not enough. People want mobility. They want to move around with laptops, phones, and tablets. So each floor also includes wireless access points. These devices provide Wi-Fi coverage and connect wireless devices to the same network. So now we have two types of connections: wired connections, which we name it as an Ethernet connection, wireless connection, which we name it as a Wi-Fi connection. And both are integrated into the same network. So now here is the key idea. Enterprise networks use a layered design. Access layer, which provides connects devices. Distribution layer, which is responsible for connects switches. And core layer in large networks are using handles high-speed backbone traffic. This layered approach makes the network scalable, flexible, easier to troubleshoot. So compared to a small Soho network, enterprise networks are more complex, but they follow the same fundamental principles. And once you understand these principles, you can easily understand much larger and more advanced networks. So, in the next section, we will go deeper into the technologies that make all of these possible. Now we need to talk about Ethernet standards. Up to this point, we have been using the word Ethernet as if it is a single technology. But in reality, Ethernet is not just one thing. It is a family of standards deployed by an organization called the IEEE. This organization defines the rules that all Ethernet devices must follow. These rules are very important because without standards, devices from different vendors wouldn't be able to communicate. Now, what exactly do these Ethernet standards define? They define several key things. First, how data is transmitted over the network. For example, whether the data is sent as electrical signals or light signals. Second, what type of cables are used? For example, Cooper cables or fiber optic cables. Third one, the speed of communication. This defines how fast data can be sent and received. So, some common standards we need to understand. For example, 10 megabit, which we see also 10 base T. This was one of the early Ethernet standards. It uses Cooper cables and supports speeds up to 10 megabits per second. 100 megabit, which we see also as a fast Ethernet. This improves the speed significantly, making networks faster and more efficient. And 1000 megabit, which we see also as a gigabit Ethernet. This is widely used today in many networks. It provides high speed performance and for most applications. 10 gigabit, which we see as a 10 gigabit Ethernet. This is used in more advanced environments such as data centers and enterprise backbone networks. Now, you might notice something interesting in these names. For example, 100 base T. Each part of this name has a meaning. 100 refers to the speed, 100 megabit. Base refers to baseband transmission. T refers to twist pair Cooper cables. So Ethernet standards are not random names. They actually describe how the technology works. Now, Let's look at the bigger picture. Ethernet has been around for decades. Over time, it has evolved continuously. It started with very low speeds, but today it supports extremely high speeds, even up to hundreds of gigabits per second. At the same time, it supports many different types of media, copper cables, fiber cables, and different cables lengths. This flexibility is one of the biggest strengths of Ethernet. It can be used in small home networks, large enterprise environments, data centers, and even service provider networks. Now, here's a key idea because Ethernet follows well-defined standards. It allows devices from different vendors to work together seamlessly. And because it has evolved over time without losing compatibility, it remains the dominant LAN technology today. That's why Ethernet is so widely used, and that is why it is a core topic in CCNA. If you understand Ethernet standards, you are not just memorizing speeds and names, you are understanding how real networks are built and scaled. So, in the next section, we will go deeper into how these standards are applied in real network environments. So far, we have talked about how data moves logically in a network, but now let's go level deeper and look at the physical side of communication. How does data actually travel between devices? This is where cables come in. One of the most common types of cables used in Ethernet networks is called UTP. UTP stands for Unshielded Twist Pair. Let's break that down. Unshielded means the cable doesn't have extra metallic shielding to protect it from interference. Twist pair means the wires inside the cable are grouped into pairs and twisted together. Now you might ask, why are the wires twisted? This is very important. When electrical signals travel through a wire, they can have affected by interference. This interference it can come from other cables, electrical devices, or even environmental noise. By twisting the wires together, we reduce this interference. The twisting helps cancel out unwanted signals and improves overall signal quality. So let's look inside the cable. A typical UTP cable contains 8 wires. These wires are organized into 4 pairs. Each pair has a specific color code, which helps technicians identify and connect them correctly. So now not all Ethernet standards use all 4 pairs. For example, 10 megabit and 100 megabit Ethernet use only 2 pairs of wires, but 1000 megabit or gigabit Ethernet use all 4 pairs. This allows it to transmit more data at the same time and achieve higher speeds. So, about connectors, we'll talk, and connectors are very important in the cabling. Most UTP cables use a connector called RG45. This connector has 4 pin positions, one for each wire in the cable. When you plug the cable into a device, each pin connects to a specific signal. Now here's where things get very important. Not all cables are wired the same way. Uh, there are two main types of Ethernet cables: straight-through cables and crossover cables. Let's start with a straight-through cable. In this type, each wire connects to the same pin number on both ends. So pin 1 goes to pin 1, pin 2 goes to pin 2, and so on. This type of cable is typically used to connect different types of devices. For example, computer to switch, switch to router, etc. Now let's look at the crossover cable. In this cable, some of the wires are swapped. Specifically, the transmit pins on one end are connected to the receive pins on the other end. Why is this necessary? Because when two similar devices connect, they both try to send data on the same pin. Without crossover, they would both be talking but not listening properly. By crossing the wires, we ensure that one device's transmit connects to the other's receive, and communication becomes possible. Traditionally, crossover cables were used to connect similar devices, for example, computer to computer, switch to switch, router to router. However, modern devices often support a feature called Auto MDIX. This feature automatically adjusts uh, the wiring internally. So, in many cases today, you can use either cable type and the devices will still communicate correctly. So the key idea, UTP cables are simple in design, but they play a critical role in network communication. They carry the actual signals that represent data. Understanding how they work helps you understand what is really happening at the physical level of a network. And this knowledge becomes very useful when you troubleshoot real network issues. So, in the next section, we'll continue exploring other types of cabling and technologies using in network devices. So let's move on to fiber optic cabling, which is one of the most important technologies in modern high-speed networking. Unlike traditional copper cables that transmit electrical signals, fiber optic cables use light pulses to carry the data. This fundamental difference is what makes fiber extremely fast, reliable, and capable of transmitting data over very long distance without significant loss. So, inside the fiber optic cable, there is a very thin strand called the core, which is made of highly purified glass or sometimes plastics in specific use case. This core is surrounded by a layer called the cladding, which has a different refractive index. The role of the cladding is to keep the light signal trapped inside the core using a principle called total internal reflection. In simple terms, the light bounces along the core without escaping, allowing it to travel long distance efficiently. Around the cladding, there are additional protective layers such as buffer coating and an outer jacket. These layers protect the fragile glass core from physical damage and environmental factors, making the cable suitable for both indoor and outdoor installation. Fiber optic communication works by converting electrical signals into light signals using a transmitter, typically a laser or LED. At the receiving end, a photodetector converts the light back into electrical signals. so that network devices can process the data. One of the biggest advantages of fiber optics is extremely high bandwidth capacity. Fiber can carry massive amount of data simultaneously, which is why it is widely used in modern internet backbones, data centers, and telecom infrastructure. Another key advantage is distance capability. Unlike copper cables, which suffer from alternation, which we say also signal loss, over relatively short distance. Fiber can transmit data for kilometers without needing signal amplification. This makes it ideal for long-distance communications such as intercity or undersea connections. Fiber is also highly resistant to electromagnetic interference and radio frequency interference. Since it uses light instead of electricity, external electrical noise doesn't affect the signal. This makes fiber more stable and secure compared to copper, especially in environments with heavy electrical equipment. Additional fiber offers better security because it is very difficult to tap without physically disturbing the cable, making unauthorized access easier to detect. There are two main types of fiber optic cables, multi-mode fiber cables, single-mode fiber cables. Multi-mode fiber has a larger core diameter typically around 50 or 62.5 microns. It allows multiple light passes to travel through the core simultaneously. Because of these, light signals can bounce at different angles, which leads to model dispersion over long distance. As a result, multimode fiber is best suited for short-distance communications, such as within buildings, campuses, or data centers. It is also generally cheaper and uses less expensive light sources like LEDs or low-cost lasers. Single mode fiber has a much smaller core, usually around 8 to 10 microns. It allows only one direct path of light to travel, which significantly reduces signal distortion and dispersion. This enables data to travel much farther distance, often tens or even hundreds of kilometers, without degradation. The single-mode fiber uses highly precise laser sources, which makes it more expensive, but it is a standard choice for telecommunication networks, long-haul links, and internet backbone infrastructures. In real networking, fiber optic forms the backbone of the global internet. Internet providers, mobile operators, and large enterprises rely on fiber to connect cities, countries, and uh, continents through submarine cables and high-capacity terrestrial networks. In summary, fiber optic cabling is the foundation of modern digital communication. It delivers unmatched speed, reliability, and scalability, making it essential for everything from enterprise networks to global internet infrastructure. Now let's talk about how data is structured is in Ethernet networking, because understanding this is essential to understanding how communication actually happens between devices. In Ethernet, data is not sent as a continuous stream. Instead, it is broken down into smaller structured units called frames. A frame is like a container that wraps the data with all the necessary control information so that it can travel across the network and reach the correct destination reliably. An Ethernet frame is made up of three main logical parts: a header, data, which we say also payload, and trailer. Each part plays a very specific role in ensuring that communication is accurate, organized, and error checked. The first part is header control information. The header is placed at the beginning of the frame and contains critical information that networking devices use to properly deliver the data. It essentially answers the question: where is the frame coming from and where should it go? One of the most important components in the header is the MAC address information, source MAC address information, and destination MAC address information. Source MAC address identifies the physical device that is sending the frame. Every network interface card has a unique MAC address, which acts like a hardware identity. Destination MAC address is identifies the intended recipient device on the local network. Switches use this information to forward the frame to the correct port. Another key field in the header is the type field. This specifies what kind of data is being carried inside the frame. For example, it can indicate whether the payload contains IPv4, IPv6, or other higher layer protocols. This helps the receiving device understand how to process the data once it is extracted. In more advanced Ethernet frames, the header may also include additional fields such as VLAN tags, which are used to logically separate networks within the same physical infrastructure. The second is data, which we say is payload. The data field is also known as the payload, is the actual content that needs to be transmitted. This is the useful information generated by applications such as a web page request, an email message, a file transfer segments, video or voice data is streaming applications, etc. The size of the payload can vary depending on the network standards and configuration, but it is typically optimized to balance efficiency and performance. It is important to understand that Ethernet itself doesn't interpret this data. It simply carries it. The interpretation happens at higher layers of the network stack, such as the IP layer or transport layer, using the TCP and UDP protocols. The third one is trailer error detection. At the end of the frame, there is the trailer, which plays a crucial role in ensuring data integrity. The main component of the trailer is the frame check sequence. The frame check sequence is generated using a mathematical algorithm called cyclic redundancy check (CRC). Before sending the frame, The sender calculates this value based on the frame's contents and attaches it to the trailer. When the frame reaches the destination, the receiving device performs the same calculation. If the result matches the FCS frame check sequence value in the trailer, the frame is considered valid and error-free. If there is a mismatch, it means the data was corrupted during transmission and the frame is discarded. This mechanism is essential because network transmissions can be affected by noise, interference, or hardware issues, even in reliable environments. Why this structure matters? This structured approach allows Ethernet networks to function efficiently and reliably. By separating control information, which we use header, actual content, which we said before, data, and validation information, which we already explained as a trailer, devices can correctly identify where data is coming from and where it should go. Transport the different types of data over the same network infrastructure. Detect and discard corrupted frames. Maintain stable and predictable communication between devices. So, in short, the Ethernet frame structure is the foundation of local network communication. Without this structured encapsulation, devices shouldn't be able to organize, route, or verify data effectively, and modern networking, as we know, it wouldn't be possible. A MAC address, media access control address, is a unique identifier assigned to a network interface card. This means that every device connects to a network, such as a computer, smartphone, printer, or router, has its own MAC address at the hardware level. It acts like a physical identity for the device on the network. A MAC address consists of 48 bits long, which we can say also 6 bytes, and it is typically written in hexadecimal format to make it easier to humans to read. Since each hexadecimal digit represents 4 bits, the full address is shown as 12 hexadecimal characters. It is commonly formatted in groups such as 00000C, 12, 3, 4, and 5, 6, or another type, four groups, four symbols, and four symbols. Between that four symbols, we have a dot. So several type of formats, but it's not changing the 48 bits, the format of MAC address. Each MAC address is divided into two main parts. The first 24 bits or 3 bytes represents the organizationally unique identifier. This portion identifies the manufacturer of the device, for example, Cisco, Apple, or Intel, etc. So the last 24 bits are assigned by the manufacturer and are unique to each device they produce. This structure ensures that no two devices in the world should have the same MAC address, at least in theory. Role of MAC addresses in networking. Uh, so MAC addresses operate at the data link layer of the OSI model. They are used for communication within a local network, local area network. When a device wants to send data to another device on the same network, it doesn't initially know the destination MAC address. Instead, it uses a protocol called ARP, which means Address Resolution Protocol. in order to map an IP address to its corresponding MAC addresses. Once the destination MAC address is known, the sender places its own MAC addresses as the source, the receiver's MAC address as the destination, into the Ethernet frame header. Network switches then use this information to forward the frame to the correct device. So McAdams has some parts, some types. MAC addresses are also used to define how data is delivered within the network. There are three main types: unicast, which means one-to-one communication. This means the most common type uh, is this one, unicast. So a frame is sent from one device directly to a single specific device. The destination MAC address in the frame matches exactly one device on the network. The second one is broadcast. So it means that one to all communication. In broadcast communication, a frame is sent to all devices in the local network. The broadcast MAC address is a special value FF. When a device sends a broadcast frame, every device on the network receives the and processes it. This is commonly used in protocols like ARP. And third one is multicast, so which means one to many communication. Multicast is used when a device wants to send data to a specific group of devices, but not everyone. Only devices that are part of that multicast group will accept and process the frame. This is useful for applications like video streaming or online conferencing. Why MAC addresses are so important? MAC addresses are essential for the proper functioning of local networks because they provide a unique identity for each device, enable accurate delivery of frames within a LAN, allow switches to build MAC address table and forward traffic efficiently, support different communication methods such as unicast, broadcast, and multicast, work together with IP addresses to enable full network communication. So what's the key insight? So it is important to understand the difference between MAC addresses and IP addresses. MAC address is physical identity layer 2 local communication. IP address logical identity for layer 3 global communication across networks. Both are required for modern networking. It helps route data across different networks, while MAC ensures the data reach the correct device within the local network. In summary, MAC addresses are the backbone of data link layer communication. They allow devices to identify each other, exchange data reliably within a local network, and ensure that Ethernet frames are delivered to the right destination. Finally, let's talk about full duplex and half duplex, which means duplex modes, which define how data can flow between two devices in a network communication. When two devices communicate over Ethernet, the way they send and receive data is determined by the duplex mode. This directly affects performance, efficiency, and how collisions are handled on the network. There are two main types of duplex mode, full duplex and half duplex. Full duplex mode, in a full duplex mode, a device can send and receive data at the same time. Think of it like a telephone conversation where both people can talk and listen simultaneously without waiting for the other person to finish. In networking terms, one device can transmit data while also receiving data on the same connection. This is possible because transmit and receive operations use separate communication paths. The key characteristics of full duplex are no collisions occur because each direction has its own channel, bandwidth is used more efficiently, communication is faster and smoother, latency is reduced because devices don't need to wait. Full duplex is the standard in modern Ethernet networks, especially when using switches, because switches create dedicated point-to-point links between devices. The second one, half-duplex communication. In half-duplex mode, devices cannot send and receive at the same time. Instead, they must take turns communicating. This is similar to a walkie-talkie system. One person speaks while the other listens. Then they switch roles. The key characteristics of half-duplex are only one direction of communication is allowed at a time. If both devices try to send data simultaneously, collisions can occur. Network performance is lower compared to full duplex and requires mechanisms like collision detection and retransmission. Half-duplex was commonly used in older Ethernet networks that relied on hubs. What's the role of hub and switches? What's the difference between them? The duplex mode is closely related to the type of networking device used hubs. Hubs are operate at the physical layer, send incoming data to all ports. All devices share the same communication medium, only supports half-duplex communication, and collisions are frequent because all devices compete for the same bandwidth. Switches are operate at the data link layer, forwards data only to the correct destination port using MAC addresses. Create separate collision domains for each connection. Support full duplex communication. Eliminate collisions in normal operation. Because of these, hubs are now considered outdated and switches are the standard in all modern networks. Why full duplex is preferred today? Modern networks use full duplex mode almost exclusively because it provides significant advantage. Higher performance, simultaneous send receive, increased throughput. So no collisions, improves reliability and efficiency, better bandwidth utilization, full use of link capacity in both directions. Scalability is suitable for high-speed enterprise and data center environments. Improved user experience, smoother applications like video calls, streaming, and cloud services. So there is a key inside the transition from half duplex or hubs to full duplex switches represents one of the most important improvements in Ethernet networking history. It fundamentally changed how local networks operate by eliminating collisions and enabling true simultaneous communication. In summary, half duplex one direction at a time, collision prone, used in older hub-based networks. Full duplex, simultaneous two-way communication, efficient, collision-free, standard in modern switch networks. This is why today networks are faster, more stable, and capable of handling large amount of real-time data traffic. Now you have a solid understanding of how Ethernet LANs work. At first, these concepts may seem complex, but step by step they become much easier. In the next lessons, we'll go deeper into each topic. If you want to master networking and CCNA, make sure you follow the course step by step. And don't forget to subscribe so you don't miss the next lessons.